Chapter 3 demo. You may need to pause to open up your demo. Again, as a reminder, you will have different values, but you can follow along with your values. Follow the instructions to do this problem. So the first thing we want to do is open this data in StatCrunch. And let me share that screen with you, so give me a second. I'm going to push this to the left just to have more space here. A random sample of 15 college students were asked, how many hours per week typically do you work outside the home? Their responses are shown in the right. Determine the shape of the distribution of hours worked by drawing a frequency histogram and computing the mean and the median. Which measure of central tendency better describes the hours worked? So here we collect the data. Now we want to look and see what the trends are, what seem to be the typical responses, etc. So let's make a frequency diagram here. You have two choices. You have to decide whether we select bar plot or whether we select histogram. So bar plot is for categorical data, and a histogram is for numerical data, or which we call quantitative data. So in this case, if it's a measurement or a count, then it's a histogram. If it's something that you can answer with this percent of the responses were like, what's your favorite juice? 10% said apple. But if it's a measurement or you're counting something, then it's quantitative. So in this case, we were counting how many hours. So that would make it numerical or quantitative in nature. So histogram, we'll select our column. We do want the frequency here. And maybe later we might need to know some values. So that one's just even, you might not need it, but it's there in case you do. Usually we won't change the binning or the way the bars, the widths of the bars, unless it doesn't match with what we have on StatCrunch. So just compute. This one goes from 0 to 5, from 5 to 10. So ours are going from 2 bars are 10, so that means it's 5. So yes, it's being binned correctly. So it seems like from 15 to 30 hours are the typical values, and some are working like part-time. So select the correct diagram for yours. That's kind of like what happened in mine, but yours might be different. It might be the same. Sometimes you'll get the same question as I did. Okay, check your answer. And now you want the shape. Ooh, this one's a tough one because it's like even here, and then it kind of looks like there's a little tail below these 3 columns are to the left. So it looks like it tails off, but this time it tails off on the left-hand side. Sometimes we might disagree with StatCrunch. I might disagree with StatCrunch. Sometimes different statisticians have different opinions. So there's a couple that I disagree with throughout the semester. And sometimes later they change them. So then we agree. But this one could be true also, roughly symmetric, like, I don't know. It could be. It's kind of, maybe I might do another diagram to see it a little bit better, like a box plot or anything like that might distinguish if there's 2 that it's kind of like, that it's close, because that could happen. And don't do this, but I'm going to do a box plot just to compare. We haven't gone to this box plot chapter yet, until the section is later. But if I do another graph that we use for box plots, I'm not going to go through the steps here, just kind of draw it. I want to see if it's skewed to the left. So see, this would be the center of the distribution, like the median, and the distance from here to one end of the distribution is a lot shorter than this distance to this end. So this one here, if I go over it like that, I could see that now it tails off to the left. Now the skew is a little bit more obvious, that on the left-hand side, there's more of a tail. So that kind of confirms it. I was about to think, well, better not now say that it's roughly symmetric, but not bell-shaped. The mean hours of work. Now, since these values are not that many, I mean, you could, to find the mean, which is the average, is you could just add these 15 numbers and divide by 15. But most likely, you might enter a number wrong, and it's a little bit of work there. So any computations, like 95 of the percent of the computations, we're going to have this technology StatCrunch compute for us. There are a couple of computations we have to do by hand, but most of them, and the ones we do by hand, are fairly straightforward, just like a fraction or something simple. If you see something where you are trying to attempt to use a complicated formula, stop, because we're not using any complicated formulas in this course. We're going to have, well, we are using them, but we're having StatCrunch compute all those values for us. So that's a red flag if you're trying to use a complicated formula. There must be an easier way, which there is. It's called StatCrunch. So mean, that medium in our diagram, the typical values, we could get that from StatCrunch. So the mean, we would go to stat. And anytime you want to get those types of values, you go to summary stats. That gives you the mean, the median, the typical deviations, like the highest value, the lowest value, etc. So we're going to have our data in the column 1. So summary stats, column 1. Let's select a variable 1. If you just want the mean, you could click on it here. I usually don't, because sometimes we want to see other values. So I just compute and look for it in our results. So here's how many n is the sample size, which in this case, there was 15 individuals that were asked this question. Here's the mean. Sometimes we won't look at here, but here's the middle. If we were to line these numbers up, or these 15 people up, and just choose the person who was standing in the middle. So that person worked 20 hours per week, whereas the average was 18. The minimum, the least amount of hours reported was 2. The highest was 29. We'll talk about these values over here. The range means the difference between the least and the most worked hours, like 29 minus 2 is 27. And there's other values here that are not here, that sometimes we use something called IQR. So I could go to options, edit, and pull that up if I needed to. Okay, but they want the mean here. And then always read to what place you want it rounded to, because that's usually a common error, that students are using the right numbers, but they're rounding to the incorrect position. Okay, so we want 3 decimal places for mine. So 3 numbers behind the decimal place. So for me, I would use all these digits. And then to round it correctly, I would check that last digit, which is a 6. And then look at the following digits to decide if that 6 is going to stay or be increased by 1. Since my next digit is a 5 or higher, then that 6 is going to be rounded up to a 7. Then check answer. If you get it wrong, then check your rounding. Could be that. The medium. Okay, so now see how this, now I don't have to go back and click on medium. This is convenient. It's here. It's 20. The medium is a little bit higher than the mean, because this person here who worked 2 hours was kind of far away from the rest of the group. So it's skewing the data to the left. So it's might be a potential outlier, maybe not, but it's still skewing the data to the left. So that's why the mean has been pulled a little bit lower than the center of 20. The mean will always be influenced by those numbers that are far away from the typical values. Let's say it was an outlier, it's going to be influenced by the outliers, and it's going to pull the mean off the center towards that outlier. So that's why the 18 is lower than if we had just been lined up all the responses and chosen the middle number. So based on this, we could kind of tell the skew. If the mean is lower than the medium, it's being skewed to the left slightly or greatly. But if the mean is higher than the medium, then it's being skewed on the opposite side, which would be the right. If they're really close to each other, most likely a symmetric graph. What measure of central tendency better describes the work hours work? Because it's skewed, what's going to be closer to the truth of the typical hours is going to be the 20, because this mean is being pulled off the center by that outlier. So the medium, But if they were the same or similar or close enough, or the graph had been bell-shaped, then the mean would be okay to use, and then in that case, we use the mean. Okay, question 2. I'm going to close this one now that I'm done using it, so I don't have many tabs opened. So the first thing we want to do is open the data in StatCrunch. Okay, the following data represent the weight in grams of random sample of 50 candies. So these are, they're probably weighing like some Skittles or some M&Ms, some that type of candy. So they took the weights of, let's say, 50 M&Ms and they weighed them. Here's the results in grams. Determine the sample standard deviation. So that's again a calculation. So now instead of looking at the data graphically, now we're actually computing. Okay, what was the average? What was that typical deviation from the center, which is the standard deviation? So we get that again from summary stats. The data is in the column. Select your variable 1. And again, I'm just going to leave this as is. So here, the mean weight, the average weight was 0.839 grams. Sometimes that's not enough information. We want to know, we want to come up with like a window of between which two values was typical. And that's what the standard deviation tells us. So the average was 0.84 grams, let's say, give or take about 0.06 grams. So this kind of gives us the that little window. Now we could say between blank and blank weights were the typical values. Round to 2 decimal places. So that typical deviation from the center to 2 decimal places. So that's 2 numbers behind the decimal. Again, look at that third digit to decide whether your second number is going to stay or be bumped up by 1 or increased by 1. So mine's 0.06. The next digit is a 2. So mine will stay as 0.6. On the basis of the histogram on the right, so they went ahead and they drew the histogram for us. Comment on the appropriateness of using the empirical rule to make any general statements about the weights of the candy. The history is bell-shaped, so the histogram is bell-shaped, so the empirical rule could be used. Yeah, roughly it is. Okay, so anytime you have distributions that are roughly bell-shaped, we can use this rule called the empirical rule. They're going to ask us questions about that in a minute. Use the empirical rule to determine the percent of candies we would expect between that fall between 0.72 grams and 0.96 grams. And the mean is 0.84, which I agree to the nearest hundredth, it is 0.84. So they calculated that for us, but I already have it here as well. So what the empirical rule says, if you have a bell-shaped distribution, then if we go from the center, which is that 0.83, and I add and subtract this typical deviation, I will capture about 68% of these numbers, 68% of the data. Now that's a theoretical percentage, but they've done enough sampling that it's a rough estimate when distributions are bell-shaped. Now this isn't perfectly bell-shaped, so in reality, you probably won't capture 68%, but it should be in the ballpark. Now, was this that first deviation? We usually do this on hand, but because I'm demonstrating it, I'm going to show you on StatCrunch. I'm going to illustrate the empirical rule for you on StatCrunch. So a way we can do that is to go to Stat, excuse me, calculators. And we're going to go here to the normal. Normal is another word we use for symmetric distributions. So you can see like a nice symmetric distribution. So what's being illustrated here is just the shape. So in here would have been like a histogram, but it's going to cloud like what we're trying to analyze. So we just kind of don't draw these original histograms or distributions. So we just kind of draw the outside of it, the shape. So in this case, the mean or the center is 0, and the typical deviations are going by 1, 2, and 3. And this notation here, it says the probability of a measurement being less than or equal to 0 is 0.5 or 50%. So what are the odds of something being to the left of the center? 50%. So here they're saying 50% is to the left of the center, 50% is to the right of the center for a distribution that's perfectly normal. Now, in my case, the mean weight was 0.84. So I'm going to use the one they gave us instead of rounding it to 3 decimal places or 4 places. And the typical deviation from that center was 0.06. So I'm going to use the answer in A to put it in here. I'm going to compute some, and then I might have an issue here that it doesn't let me do it. So here I might have to put some number here. So let me compute. And I want the center to be labeled on my diagram, if I'm going to use the empirical rule, as 0.84, which it's not. So up here, there's a little window that says 68, 95, 99.7 ticks. And this is the empirical rule. So I'm going to click on that. And now when I do that, you'll see that the 84.84 is now in the center. So if I go up by 0.06, I'm going to land on 0.9. And if I take 0.84 and I subtract a deviation, which is 0.06, I'm going to land on 0.78. So if I wanted to do this and draw it on paper myself, I would take the 0.84, add 0.06, which equals 0.9. And then I would take that 0.9 and add another deviation of 0.06, and I would get 0.96. And then I would take 0.96 and add another deviation of 0.06, and I would get 1.02. And then I would do the same to the left. Instead of adding 0.06, I would take that 0.84 and subtract 0.06 each time. So this kind of saves me some work. So the empirical rule says that when you added one deviation, remember how the previous picture had 0, 1, 2, and 3? So if you add one deviation, if you add one standard deviation, 68%, this one's for the first standard deviation, 68% of the data should be captured. If you go another count, 95% of the responses should be captured. And by the time you go to the third one, almost all, 99.7 roughly, that's a theoretical value, but mostly all of the responses should be captured by the time you go to the third one, because the distribution is nicely symmetrical. If it didn't let us do this, I would just put the mean here. I would put that number here and then compute. So if you're getting an error, just go in here and just put that number here and compute. It's just going to shade 50% again, but at least it'll let you compute the tick marks. Sometimes that'll happen when you get an error message because StatCrunch wants you to put something in. So if that happened, that's a way you could fix it on your end. Okay, so when you use the empirical rule, you have to use these numbers. Okay, so the empirical rule states that if you go out one deviation, it's 68%, 2 deviations, it's 95%. By the time you go to the third deviation, you've captured almost 100% of the data. So we need to see, using these 3 numbers, what theory says we should capture in terms of these weights. So it's 0.72, I see it here, and the 0.96 would be here. Be careful on yours, it might be the first count, it might be the third count. On mine, it's the second one that's away from the center on both ends. But yours might be the first. So my second deviation here, this is for the first deviation, this is for the second. The second deviation says I should capture 95% of the data. If yours is only up to the first deviation, then the empirical rule says that you should capture roughly about 68% of all the values. So mine went to the second one, so I'm going to put 95. And in this case, they have a percent sign here. If they didn't, then usually they want the decimal version of it, so it would be 0.95. But here they want the percent. So yours might not be 95, it might be 68 if yours just went to the first count. Just be careful about that. Now we want to determine, okay, that was what theoretically we should expect in the ballpark of 95. Now what actually happened in reality? How many of these candy weights were between 0.72 and 96 grams? Inclusive means including these 2 weights, including the ends. So let me move this to the side. I'm going to scroll all the way back to row 1, just so I can see everything. I guess I'm going to close this for now, so a little bit cleaner. We need to count how many were between those two weights, but they're out of order, so it's going to be difficult to count. So I'm going to sort this column, put them in order from smallest to largest. So to do that, it could be found under the tab Data, and then select Sort. You could leave it on all columns, or you could go to Select Column. I'm going to select column variable 1. You could replace the current column, or you can create a new column. I usually tend to create a new column. You also have to select this sort criteria, because sometimes there's multiple columns. So you want to select the one that you are sorting. So variable 1. Ascending just means to go from highest to lowest. If for some reason you want to go from, for ascending means from lowest to highest. And if for some reason you want to go from highest to lowest, you can do descending. But I'm going to keep it on ascending. Compute. Okay, this just tells us what they did. Let me close it. I don't need that. So now it's all the weights are sorted. So you can see it's increasing in quantity as you go back up. Now there's 40. Instead of counting all the ones that were between those two, it's easier to count the ones that weren't, because there's not that many that weren't, and then kind of subtracting it from the 50 candies. So on the lower end, it's between 72, so inclusive. So I only have one that's not from 0.72 on. So there's one on the lower end. And let me see on the higher end what was not between 0.96. So on the higher end, I have 2, these 2. So in total, I have 3 from the 50 that were not in between there. So that would leave 47. So that means the rest of them were between the weights of 0.72 and 96. So I'm going to do 47 now divided by 50. You can do it in your head, or if you need a calculator for that, just enter it in the calculator. Also, over here, there's this button, Get More Help. There's a handy little calculator there. It's better. It's probably better to use like a scientific calculator. It's easier to use a manual one than one here, but then you can enter it on your calculator here and get the decimal version. So in my case, it's 0.94 for mine, which was pretty close to the theoretical 95. Now yours might have been 90%, so yours might be slightly different. Might have been 99%. It shouldn't be like 10% or 15%. It should be a lot, like almost everybody, 95%. So it should be in the 90s, most likely. Maybe it could be 85 or 87. In reality, when we would do these in real life. So they want the percent. So 0.94 times 100 is 94%. So I would now multiply that proportion by 100 to get the percentage. Sometimes the numbers are a little bit more messy. So oh, it cleared it for me. You could just multiply that answer by 100 on your calculator, and then you can get the percentages. This was a very a good sample size, so we were kind of close, but it should be in the 90s. But if we had like a smaller sample size, then it might be a little further away from the expected 95%. Or if this was more rougher in shape, then we might not get like close to 95 as well, because it is dependent on how normal the distribution is. The more normal, the closer we'll get to the theory. The less normal, the less we'll be closer to theory. And then now I want to know the empirical rule more than 0.9 grams. Okay, so I'm going to go here to my StatCrunch results because I put them away. Results hidden. I had the summer stats, the normal calculator. But we did the normal calculator to use the empirical rule. Here we go. If for some reason it disappeared on you, then just go back, listen to that recording, the part where I explain how to get here. more than 0.9. Okay, so I have to look at you don't do it here, because this will give me a more precise measurement. We just want to use the estimates from approximately what in the ballpark figures what the empirical rule states. Okay, so more than 0.9, which is here, is my first deviation to the right. So that first deviation is 68. So 68% is captured. Let me show you visually here. I'm going to put the 68% here so that we can see. Oops. Sorry. I'm going to do a between. This is easier on paper, but just to illustrate it here. Okay, let's do compute. Okay, so what I told StatCrunch, you don't have to do this, but just to illustrate this. Okay, what I have shaded is 68% roughly because the empirical rule says that if you go out one standard deviation, you'll capture 68%. Notice here that it should be between 0.78, 0.9. StatCrunch will do it a little bit more precisely. So we want to ignore that. Okay, so we want to know how many weigh more than the 0.9. So I want to know what percent are in this part. Now the whole distribution should account for 100% of the data. So from here to here is 100% of the data. Now the reason this isn't like closed down because we don't know where the highest value is and the lowest value is, so we just kind of leave it open because we could have an actual value that is more than 3 standard deviations, so we kind of leave it open-ended there. Okay, so if this whole thing is 100% and this middle piece is 68, then 100% minus 68 leaves 32% for this white section. But I only want to the right of 9.9 because I want more than 0.9, so I want the higher end. So if this white section is 32%, I could take that 32%, divide it evenly into those two spaces, and that would mean that 16 would have to be to the left of that first standard deviation, and 16% would have to be to the right of that first standard deviation. So theory says that about 16% of all the candies should weigh more than 0.9 grams. Now, if yours went to the second deviation, then that's a little bit different. So in case your question was the second deviation, let's say, which is the 95 percentile, change this to 95 just to illustrate that for those students that might get that picture. So here I have in red shaded up to the second deviation. Theory says you should capture about 95% of all weights or all data values. So in this case, we do 100 minus 95, which is the red section, which would leave 5% for this white area, a lot less because now we're taking more space here. So if there's 5% for these two sections, and I divide that evenly into 2, then I get 2.5. So this will represent 2.5% of all the values, and this little section will represent 2.5% of all the values. So your answer would be 2.5 if your question asked for the second deviation. Now we're going to determine the actual percent that weighed more than 0.9. So let me close this, put it away for a minute. And since it's already in order, it just said this more than 0.9. So I just have to scroll down to the bottom and just count how many were more than 0.9. So in my case, it was these. So 1, 2, 3, 4, 5, 6, 7, 8. So in my case, 8 out of the 50 were weighed more than 0.9. Which in my case, if I change it, if I divide that on the calculator, it's 0.16. If I times that by 100 to change it to a percent, then I get 16%. Because they want the percent, not the decimal. The decimal version, we call it a proportion. So the proportion is 0.16, the percent is 16%. Now, theory said 16%, and in actuality, it was 16%. But yours might be a little bit different. But it should be low. It shouldn't be like 70 or 50 here. it should be in the ballpark of 60%. Close that. Okay, let me open this in StatCrunch in case we need it and share that with you while you pull up the next question. Suppose that a customer is purchasing a car. He conducts an experiment in which he puts 10 gallons of gas in the car and drives it until it runs out of gas. He conducts this experiment 15 times on each car and records the number of miles driven. So maybe he wants to see which vehicle of the two is more fuel efficient, which one you can get more mileage out of. Uses less gas, in other words. And he's comparing two cars, and he takes 15 measurements on each car. So he puts 10 gallons of gas, he waits until it runs out, and then he measures, or he records how many miles he was driven. So, it's the same car. Why is there each time that he did it, he got different responses? Well, usually it'll vary because maybe the road conditions wasn't stopping and going a lot, like traffic. That's going to influence the gas consumption. So that's why it varies from each time he filled the tank. But they're all in the ballpark of each other. Describe each data set. So let's now compare. We want to know the shape, the center, and the spread is like the typical deviation from that center, or how much it typically vary from the center. Okay, so we want the mean for both cars, so the average. So we're going to go to stat. Let's open this in StatCrunch. Remember, click on to copy the table, this table, open in StatCrunch, which I already did over here on the right. Okay, so go to stat, summary stats, whenever you want to get the mean, the median, all that. Our data is in columns, so click on columns. And then I want both of these. If I just click on this, just car one is going to be pulled up. So make sure you highlight both. You can, I hold down on a PC, I hold down the control key, and then I just click this car two while I'm holding down the control key, and that will show up on a Mac. You might have to do it a little bit slightly different. So just kind of figure out on your computer how to do that. Again, I'm not going to mess with this. I'm just going to compute it. Because right now I just want the mean, but for others later on, I might want the others, other values like the median, because that's what they have us do that in this car. In this example, I should say. So car one had 15, car two had 15. If you can't get both of them to show up, just do one at a time. It's not a big deal. Okay, so the mean for car one, it says round to 1 decimal place. So I always read that rounding. So for me, it's 246.8. And then for car two, to 1 decimal place, I would stop at the 7. The next digit is a 3, so I'm just going to leave it as a 7. I don't have to round it up. So just based on this, it looks like they're very similar, very close. That I wouldn't say one is significantly better than the other, just using the center measurement of mean, because that variation could have just happened naturally, like the road conditions or traffic. So if one was significantly higher than the other, I might say, okay, yeah, this one gave me more. But if that's all I had to base on, that was the only thing I could say car one right now is the winner slightly. Okay, median for each car. So that means if we ordered all these numbers and we took the center, that would be 256 for the first car for mine and 251 for the second car for mine. Again, it seems like car one is slightly a little bit more than 2. You just got 5 extra miles on average. That's a little bit more significant, I guess. Now, these two are both measures of center. Sometimes we use the mean as a better estimate of the truth, or like all times you're going to be filling up the tank and driving, or sometimes the median is better. So you have to make a decision depending on your data, which one is the truer value to the actual mileage you're going to get. In this case, it depends on whether the data is skewed or not. So if it's skewed, then we'll go with the median because that won't be affected by outliers. But if it's roughly symmetric, then we would use the mean as our best measurement to describe the center of the data. So those two are used for center of the data. Mean, if the data is distributed, the distribution looks bell-shaped. Mean, medium, if there happens to be like an outlier. Okay, the range, so that's here. So the range is 78 for car 1, 159 for car 2. Now there, it's a big difference. So we have to think, okay, what is range describing? Range is the difference between the lowest and the highest value, like the overall spread. Like, so the difference between the least amount of miles driven and the most miles driven for car 1 was 78 miles per gallon. For car 2, the difference was from the highest, which was 313, to the lowest was 154, which is 159. So it seems like the car 2, there's more variation in the numbers. That means these numbers were more, there was more variation from between these values. Like the difference between the lower numbers and the higher numbers was more spread out than these. These seem to be more consistent. They were all in the 200s. They weren't as spread out. So that's consistent means maybe like more reliable then, because then you can kind of know that, you know, you're going to get 200 and something here, where here it could be as low as 154 and as high as 313. That's a huge difference in terms of what you can expect out of one tank of gas, and that's not as reliable. So sometimes it's not enough just to know the center. Sometimes if we look at other values, that can kind of help us make better decisions. Okay, the sample standard deviation. So here it is, STDDEV. And then this one says to 1 decimal place. So for car 1, mine is 25.5. I have to round it up because that next digit is a 9. So that 5 becomes a 6. And then for my car 2, it's 46.3. So 46.4 for mine. So I have to also round it up because my next digit is an 8. So sample standard deviation. So this is, the range is the overall spread, how wide, the difference between the largest and the smallest. The sample deviation is like your typical spread. Typically, for the typical values, how wide are those? So for the typical values, like there's only a 25 mile per 10 gallons or per tank difference versus a 46. So this again is more spread out than this one for the typical values. So now I can say, this one we use with the mean, like if your data is symmetrical. So I would say for car 1, I can get 256 miles on a tank, give or take 25 or 26 miles. For car 2, oops, I'm looking at the wrong value. Here it is, sample mean. For car 1, I can expect about 247 miles on a tank, give or take about 26 miles. For car 2, I could expect on average 246 miles, give or take 46 miles. So that window of what's typical is a lot wider for this one if I wanted to just capture the typical values of what we could expect. Continue. Now, if our data was skewed, then I wouldn't go with mean, I would go with mean, and I would say for car 1, it would be 256 miles per tank, give or take something, and for medium car would be 251. And it turns out that the typical values, if your data like it's skewed left or right, and you're going with the medium, and it ends up being these last two values here. So for car 1, the typical values, if it's skewed, then is 256, but that little window of typical values would be anywhere between 233 and 264. And for the car 2, when the medium's 251, the typical values would be 231 to 258, 287. So this would be the little window for car 2 as to what the typical miles per tank you could get. And that one's more spread out than this one. I could figure out that difference. It doesn't give me the difference here. The difference here, I could subtract them. We give that a name. It's called IQR, and I can have StatCrunch, give me that as well. You don't have to do this, but later on in a future problem, you can have like this one here. So if I add that one, the typical values, if you look at these, the mediums, based on the medium, it's 56, and for car 1, it's 31. So it's still consistently, it seems like car 2, there's more variation in the numbers. They were more dispersed, more spread out. Okay, so now based on, if it was just like, if I had just based it on the mean, I wouldn't really say that there's a significant difference, or even in the medium, maybe a little bit, car 1 a little bit. But now analyzing all these other numbers of what it typically deviates by, it would make more sense to choose one car versus the other. So let's see what the choices are here. There's very little difference between the two cars. Well, if I just looked at the mean, yes, but once I start analyzing the spreads, that's not like the overall range and the typical range. Here is the overall range and the typical range, then they are different from each other. So I would buy car 2 because it has a larger range. Car 1 because it has a lower standard deviation, hence more predictable gas mileage. Car 1 because it has a lower mean gas mileage. There's very little difference. So not D. Car 1 we said was slightly better because the ranges, the overall range and the typical range were less. So this is more reliable. These are more spread out. That's when you get a bigger range and a bigger deviation from the center, it's because the numbers are more spread out, further away from each other. So car 1, not because it had a lower mean, because that wasn't enough, it was because of the standard deviation. The spread from that mean, the deviations, they were more consistent, more reliable. Five-number summary. Okay, so the 5-number summary is 5 numbers that we use to summarize all these numbers. So from all these numbers, we choose five important numbers. There's a formula sheet, the formula sheet that I posted on Canvas and the StatCrunch instructions. You can always use those on exams, but the formula sheet will have this on there. So if you forget, you could just look at that. I would recommend that you print those out. So here we are, the 5-number summary. So you just have to know it's the smallest. So let me open this in StatCrunch and share that screen with you. So go ahead and open it on your end. Okay, so we're going to go to stats, summary stats, columns. We're going to get the select variable 1 and then compute. If you just go by the default ones that are going to show up. We use the 5-number summary when we're depicting the distribution in what's called a box plot instead of like a stem and leaf or a histogram. This is for numerical data only as well. So for quantitative data. So we make the box plot based on these 5 numbers, or we construct it. So the first number, the first important number is the smallest number in the entire group. That's going to be the min. For me, it's 43. The last number is going to be the maximum, the highest number in this group, 69. And all the numbers between here will be numbers between the lowest and the highest. What goes in the middle here is the medium. So this is when we're summarizing our results for skewed data, left skewed, right skewed. I mean, we can use it for symmetric graphs as well, but most of the time when we apply the medium, it's for skewed graphs. And then this number, so we line up all the numbers, all the results, like let's say all the ages of these world leaders on their day of inauguration. So we would order the ages, and then this would be the first person standing would be the lowest, the last person standing would be the eldest. In the middle whoever's standing in the middle, their age would go here. And then what we do, we just see who's standing in the middle of between these two of these, however many people there are. So that person there, we call that number there, we call the first quarter, 52 in my case. And over here, we call it the third quarter, which is 67. I'm going to show you that we could have just drawn the box plot and achieved these 5 numbers, so we don't even need to do this. So what a box plot does, it takes all the data. Let's say there were 16 for make it easier. And it divides it into 4 equal groups. So 16 divided into 4 equal groups means that this is my first group of 4. That would be group 1. So this cutoff here is the first 20. So if I put them in groups of 4, then each group has 25%. So this is the lowest 25%. It goes from the minimum to the end of the first quarter. And then here's my next group of 4. So this goes from the first quarter to the middle. So this they're not in order, but this would be the middle. Let me just put them in order because then it makes a little bit more sense. You don't have to do this, but I'm just illustrating. Okay, so these 4 ages, now they're in order, would be the first quarter, which contains 25% of all the numbers, roughly. If there was 16, I'm trying to divide it into 4 groups evenly. So then this would be the first quarter. So 52, let's say, was there. And then this would go from the first quarter to the middle. So the middle would be 61 there. If there were 16 people, it'd be halfway between 61 and 62, so 61 and a half. And then the third, from the middle, which is the medium, to the next group of 4, let's say, would be the third quarter. So it goes from the medium to Q3, the third quarter, which is 75% of the data now. And then the last 25% would go from the 67 to, like, let's say, the 16th person. And in this case would be, I put the wrong number, I just saw that right there, would be 69. Sorry about that. So sometimes I say things wrong, but I usually will catch my mistake afterwards. So my maximum is 69. So at some point I'll say the right thing because then StatCrunch will mark it wrong. So they should go in order. So that's actually a good thing to make sure that they're going in order from the lowest to the highest. 43, 52, 61, 67, 69. Now it's in the correct order. You were probably wondering, why did she put that? All right, so check answer. Plus they tell you here, make sure it's in ascending order. Now we're going to draw the box plot. So I could have gotten all that information from the box plot as well. Since it's a graph now, that's going to give us a summary of the data in graphical form. Go to a graph, go to box plot. Select variable 1. If normally the graph will be vertical, so if you want it horizontal like this, you click on draw horizontal boxes horizontally. If you forget, you can always go back and do edit and click that box. So 25% of the data was from here to here. Another 25% of the data was from here to here. Another 25% here and another 25%. The fact that, okay, if there was 4 people in each group, why is this space longer than this space? It's because the last 4 people had less variability in their responses. There was less spread, remember, like the cars. So like, let's look at the last 4 people. See, it went from 65 to 69. That's a 4-year difference between these two. Whereas the first group of 4, the first quarter, it went from 43 to 52. So that's like a 9-year difference between the first 4. So that's shown as a longer space here. We call these whiskers, a longer whisker here. So if you had like a box here and a box here, the first box, we don't shade it. So we just draw like a line to the least response to that first quarter. And then the last box is not shaded, like the last box would be here. We just draw a little whisker from the third quarter to the last person here. And the reason we just shade the middle 50%, the 2 middle 25% in here, is because then now this represents the typical values. The people that were in the middle were the typical ones. So the typical age is anywhere from Q1 to Q3. Now notice when I'm moving this around, some yellow boxes are popping up. So if I just put it somewhere, Remember I said I can get the 5-number summary here. So this is nice because for box plots, it gives us the important numbers. So the number of values, N is 15, that's the sample size. The IQR was how far apart the typical spread is, like the typical ages, like from Q1 to Q3. So for the typical ages, there was only a 15-year difference. Now the overall spread from 43 to 69, that's like a 26-year difference from the youngest to the oldest. But in terms of the typical ages, it's a lot less. The lower limit is the min, 43. There's Q1 52, the medium 61, the Q3 67, and then the upper limit 69. So what's nice about doing it this way is that it gives you those 5 numbers in order, and I don't have to fish for them like in the summary stats. The only numbers that you have to make sure you don't use is the number of values 15 and the IQR is 15. That's just extra. You start with the min, which is 43, and then just write those 5 numbers, which are the same that I had over here. Okay, but now the shape. Sometimes they're significantly different from each other, so it's easy to choose. Be careful. Sometimes they give us 2 diagrams that are very similar, and in that case, we have to kind of really pay attention to where the values here are, like the cutoffs. But this one's kind of obvious. And then the way we would look at the shape is to kind of start it from here and kind of view it like this. And I could kind of see kind of tails off on the left-hand side. You can kind of also tell the shape because usually the distance from the center to the end of this whisker is shorter than, for my case in anyways, than the distance from the center to this side here. So it's longer towards the left, more variation on the left, so it's skewed to the left. The shape can't be determined. I don't think we have any of those, but it's true that sometimes it's hard to tell. And sometimes it's a clearer picture if you do one of the other, the other graphs like the histogram or the dot plot. And sometimes you can tell the shape a little bit better from one of those. Sometimes the histogram is kind of hard to tell what the shape is, so then we draw the box plot. Okay, so then didn't I just do this one? Oh, it's incomplete. What did I do here? Let me see. Okay, so let's might be, let me see, which one was this one? It could have been that I just didn't record it. Okay. For some reason it didn't record it. I don't know if I didn't finish it. Let me show completed here. No, it seemed like it was complete. Okay, it just didn't record it for some reason. I didn't save it or something. Okay, but regardless, we already did it. Let's go to question 5. So, open up your data in StatCrunch. The data at the right represent the number of chocolate chip cookies per cookie in a random sample of a name brand and a store brand. Complete parts A to C below. So I guess somebody wants to know if it's worth it to buy the name brand and pay a little bit extra if they're just interested in the amount of chocolate chips. I want the cookie that has more chocolate chips in it. I don't really care about the batter. I just want more candy. So then you want to compare, like, is it worth it buying the name brand? Do I get more chocolate chips, or can I just buy the store brand and get roughly the same? So here's some analysis that will help us with that. Just a little bit wider here. Draw side-by-side box plots. And we're going to use N for the name brand and S for the store brand. So let's go to graph, box plot. Again, I'm going to hold on my control button because I want both of these, so I can select both of them simultaneously. And then I want to draw my boxes horizontally. So compute. Don't forget, you can always pause the video if you get a little bit behind. Now, the only tricky part here is that the store brand's on top and the name brand's on the bottom, where here it's reversed. If that's going to be too confusing for you, what you can do is go to Options, Edit, and then I want this reversed. So I want the store brand first. I'm going to click on store brand. Well, I'm going to click on store brand over here. That didn't work. Store brand first. And now I'm going to hit the control button and select the other one. So I'm reversing the order there. Compute. And now the name brand's on the top and the store brand's on the bottom. But if you're okay with that. So the name brand, kind of like this, this first quarter here is kind of like lined, not exactly, but lined up with the middle here. So I kind of want to choose and see which one is kind of like that. So let's see which one it's not. So, or if I look at the centers, like the centers to the left of this one. Well, they all are, but this one's significantly. See how this medium here lines up with the first quarter? It's to the left of the first quarter, and this one it isn't. It's to the right of the first quarter, so it can't be this one. So it's between these two, because this space here is really wide, which we don't have over here. So it's between these two. Now the difference between these two is that this one has a long whisker here, and this one has a short one. So in this case here, this whisker here, that lower limit is 22. That's the lowest number. And I want to choose the one where the lowest number is 22, where here, see how the lowest number is like between 10 and 20, which is 15. You can also, like, if you want to see it bigger, you can put on that and see it a little bit bigger. So you could see that, you know, yeah, it looks like it's 21. Or I want to put it back. I don't know how to put it back. I wanted to bring it out like this. So shouldn't have done that. There should be a way to put it back, but I don't know what it is right now. But or you could do this one. I like doing this one here, where you can pull it. You make it really big. So if you need to do that, then you can do that. So this was picture A. This picture is going like from 10, 12, 14, like 15 here. And this is obviously bigger than 20. So this one's nice because then I can close it, and I didn't affect this, but I guess this one I can't really go back to it. Check answer. Maybe on your end you can. Does there appear to be a difference in the number of chocolate chip cookies? They changed this recently. I always think about this because the name brand seems to have more. The medium is 26, whereas the medium here is 24. Now, a difference between two chips doesn't seem like a lot. So that could have happened by chance variation. That's going to happen naturally from sample to sample. So in my case, I wouldn't say that that's significant, but you could see it. The general trend seems to be higher for name brand than store brand. But a lot of times we do look at that medium. So just visually, it does look like the name brand is a little bit higher. So, but then the mediums are different. So let's see, don't press it. I'm going to check it first. If I get it wrong, then you can say, okay, then that's what they went to. So there's some ambiguity. So I'm going to say, yes, the name brand appears to have more chips per cookie, but don't check answer. No, there's no difference. Well, there is a difference. I don't know if that difference is significant. Yes, the store brand. No, the store brand doesn't have to have more. So it appears to have more. Is that significant? I don't know. So we'll go with that. Okay, so yeah, that's the one they wanted. Does one brand have a more consistent number of chips per cookie? See, my opinion would be that they have roughly the same amount, But again, wait until I click it on because I don't think compared to the mediums, it's not a big difference. But if I look at the entire typical values, typically the store brand has between Q1 and Q3, so between 21 and 27. And this one has between 23 and 29. See, I wouldn't really consider that a big difference, but I guess the cookies are small. To get 2 chips extra might change the flavor. I don't know. But let's see, if I chose yes here, let me click it first. Yes, the name brand seems to have a more consistent number of cookies. Okay, so yeah, that's how they're analyzing that particular question. It looks like that one was completed. Let me double check that we answered all the questions. Okay. All right, this one just it didn't record it because I didn't save it or I was talking too long. So that concludes this demo.